Hello and welcome to our new section on area of regular polygons. We do need to recall what regular means and what a polygon means. So start off with polygon. Polygon is an n-sided figure, whether it's a triangle, square, rectangle, it just has n amount of sides, which means it has n amount of angles. So for instance, if it is a 5-sided figure, it is a pentagon. Pentagon has 5 sides, and we could actually calculate the number of the sum of the interior angles for that pentagon. Regular means that all the sides and the angles are congruent. So that means in this pentagon, we could actually solve for what one interior angle is, because all the angles are congruent. And we'll do that. We probably won't do a pentagon, we'll probably do a hexagon because it's a little bit easier and it's better for the area equation. And you'll see what I mean in just a second. So the area, the sum of interior angles of a polygon can be calculated, if you remember, by taking the number of sides, n, subtract 2 sides, and multiply by 180 degrees. So like a triangle has 3 sides, 3 minus 2 is 1, times 180 is 180. Or if you take, for example, let's say an octagon, something a little different. Octagon, we know, has 8 sides and is equal to 8. So we take 8 minus 2, multiply that with 180, and we end up getting 6 times 180. If you want to do this, that's perfectly fine, which is equal to 1080 degrees. Okay? So if it's a regular polygon, we would know all, like I just said, all sides and angles are congruent. So that means if there's in an octagon, there's a total of 1080 degrees, we could divide it by the number of angles there are, which is 8. So we could take 1080 in this particular case. Well, here, let's do this. The normal equation would go as follows. Regular polygon. No, I take that back. We'll start here. So here, one interior angle of a regular polygon would be equal to n minus 2 times 180. So that's still the typical equation for solving for the sum of the interior angles, but we divide it by the number of angles there are in that equation, or in that polygon. So we could say, in this particular case, we know that if it's an octagon, we already know how many total degrees there are. There's 1080 degrees. We would divide that by 8, and we would get one interior angle of 135 degrees. So this is one interior angle, which means all of the angles are 135 degrees on the inside of a regular octagon. The exterior angle of a regular octagon is actually a lot easier, because if you remember the exterior angle, so this actually would be good to know. So this is another quick recall. The exterior angle, so this is a sum of exterior angles. This is always going to be equal to 360 degrees. So if you want to, you could actually just take 360 degrees and divide it by the number of sides there are, or number of angles there are. So in this octagon example, we could take 360 degrees, divide this by 8, and we should get an angle measure of 45. If you also remember, in a regular polygon, the interior angle and exterior angle are congruent. So this is one exterior angle, and they're not congruent, they're supplementary. So 135 plus 45 is the 180. Okay? So that is a good recall that interior angles and exterior angles are supplementary. Now, to the main course of this lesson. So that's all review. Okay? We've worked with polygons before. We should hopefully quickly recall this. But when it comes to regular polygons, it does get a little bit, I wouldn't say dicey, but it does get a little bit, it can be a little bit tricky because you have to work with some new definitions. So the area of a regular polygon states is 1/2 times the apothem, which is a new term, we'll define that in a minute, times the perimeter. Perimeter we should know. We could calculate the perimeter of any shape, especially if it's regular, because all sides are congruent. So that's your equation for a regular polygon, okay? And let's do some definitions. In blue, let's define what an apothem is. An apothem is a segment from the center of a regular polygon, and bisects and is perpendicular. Let's just use a simple, and is perpendicular to one of the sides. So it is a perpendicular bisector just to one of the sides. So, well, I'll show a diagram for this in just a second. We also need to know what a radius is. So a radius in a regular polygon is a segment. I'm color coding this on purpose because the diagram will be color coded from the center of a polygon, a regular polygon, to an endpoint on the polygon and bisects the angle. Okay, so a lot going on here, 2 new definitions. Let's work with a regular hexagon as our only problem for the day. So let's say this is our only example. A regular hexagon. Regular hexagon entails that we have 6 sides. So that means we could draw one out. Does not have to be perfect. 6 sides. All sides are congruent, which is nice. All angles are congruent as well, because it is regular after all. And we would piece this together by saying the apothem. Let's do a black dot in the middle, showing the center. The apothem is a segment from the center to one of the sides, and it is perpendicular, and it bisects this. So, for instance, if this had a length of 10, this would break up into 5 and 5. So that's what it means by it bisects it. So we could put 2 ticks here to illustrate that it is bisecting that particular segment on the side. Okay? Then, let's make sure this goes all the way to the center. Then we could draw a radius. A radius goes to one of the endpoints. So the endpoint would be right here where pretty much we have a change of direction. And there is your radius, because if you think about it, if we had a circle going around this, it would be a radius of that circle. Okay, so here's your radius. In other words, the radius is the hypotenuse, because we have a right triangle here, and the apothem is one of the legs. All right, so there we have it. That is how we need to break this down. Okay. The other nice part about this is, if it's specifically a hexagon, we could actually solve for one of the interior angles. Okay, so we know that a hexagon has 6 sides, so we take 6 minus 2, multiply that with 180. That would be equal to 720. Take that 720, divide it by the number of sides there are, or angles there are, divided by 6, and we get one interior angle is equal to 120 degrees. So if we did this angle, every angle would be 120 degrees. Okay, I'm not going to do it for every single one, but this angle in particular is getting bisected. That's part of the definition of the radius. It is bisected. It bisects the angle. So instead of putting 120 here, I could actually put 60 and 60. And now we have actually a 30, 60, 90 triangle. So if you don't see it, hopefully you do right now. Right here, we have a 30, 60, 90 triangle. And this is how we could actually piece this together, because if we hypothetically have a side length of 10, that means all side lengths are 10. We have 6 sides, so the perimeter of this would be equal to 60. Okay? We could also then continue and solve for, well, we know what this side would be, theoretically. This side, I'm going to do this in pink. This would be a 5. And theoretically, this should also be in pink. Sorry if you already wrote that down. This would be 5, which means that's the 30-degree side, or the B side, because this is 30 degrees. So this is the B side, which means this is the B root 3 side, and we would have 5 root 3. And now we would actually calculate the apothem. Apothem is 5 root 3, and we could throw everything into this equation. So let's do that. Might as well. We're already pretty much there. So let's say area is equal to 1/2. We already said that this is 5 root 3 because it's a 30, 60, 90. So the apothem is 5 root 3. The perimeter, we said, was 60. And we just multiply accordingly. Okay? So area is then equal to, I'm going to multiply these two instead. 1/2 of 60 is 30. 30 times 5 is 150. So we could say 150 root 3 units squared. So in this particular case, we would have 150 root 3 units squared. We could do this for any polygon as long as we calculate the apothem, and we have some other piece of information such as the radius or one of the side lengths or even the perimeter. So that is it. We're going to work with a lot with different polygons, not just hexagons. So be prepared to work. We're going to have a lot of trig, a lot of 30, 60, 90. Probably a lot more trig than you think. All right. So two new definitions, one new equation, and a lot of review. If you have any questions, please ask, and I'll see you in the next one. Bye.